Hello! We have focused on creating a next generation high altitude, long endurance, unmanned aerial vehicle. I'm Jeremy Trilling.
And I'm Megan Melito. So we based our design on the U.S. Air Force RQ-4 Global Hawk. This Global Hawk has a 65-foot service ceiling, sensor payload of over 3,000 pounds, and an endurance of over 36 hours. The Global Hawk is a useful tool in intelligence for the United States.
With the global climate crisis looming, our literature review focused on aircraft that utilize hydrogen as their fuel. The use of renewable hydrogen provides a direct path for large, long endurance, zero emission flight. While size varies among these aircraft, the notable difference lies in significant increases in endurance when using liquid hydrogen as their energy source. The Phantom I, designed and built by Boeing, features two modified car engines coupled directly to propellers and more than triples the endurance of the jet fuel powered RQ-4. The AeroVironment built Global Observer takes endurance even further with its 168-hour flight time enabled by a hydrogen internal combustion engine generator that drives a set of 4 electric motors on the leading edge of the wing. Companies such as Airbus are now developing hydrogen combustion airlines and cargo planes to meet climate and industry goals.
With most mission needs being met with the current generation of Global Hawks, the area for improvement seemed to be clear. Focus on endurance. This would allow for longer missions with greater intelligence presence with less downtime. As you can see in the percent change column, we focused on the range, endurance, and carbon emissions of our aircraft. We had many issues trying to calculate the weight estimation due to the specific fuel consumption of both the baseline and our aircraft. The initial iteration was much smaller than the baseline aircraft due to the liquid hydrogen fuel. And the refined estimation, however, increased larger than predicted from the initial weight, likely due to take into account the fuel tanks added to our aircraft.
We used XFLR5 to narrow down the choice of airfoil and settle on the NASA LRN 1015 as it provides a good performance characteristics, including a coefficient of lift of 0.75 at 1 degree angle of attack when a coefficient of 0.6 is required at cruise. The airfoil choice features high lift over drag at the required flight speeds with laminar flow qualities and a thick center adequate for a tall composite spar.
Wing sizing was refined based on the lowest wing loading during a mission for most conservative results. We focused on a high aspect wing ratio to reduce the induced drag and support the long endurance missions. These are the values we converged on.
The two concepts shown here illustrate the use of different propulsion systems. The one on the left shows a potential hydrogen combustion engine configuration similar to that of the Phantom I, while the concept on the right uses a hydrogen fuel cell system to power twin electric motors mounted on nacelles. Here we analyze a carbon fiber reinforced polymer box spar using FEA software with a G limit of 3. Using these loads and dimensions, we are able to assess the minimum safety factor as 1.5 and the maximum wing deflection as 4.4 feet.
Using the wing loading calculations, we were able to calculate the thrust to weight ratio for each mission leg. The required thrust of takeoff could be altered by changing the length of the runway.
With required thrust specifications now calculated, we were able to pick the Rolls-Royce AE 3007 turbofan for our propulsion system. With a max thrust of 9,500 pound force and a respectable thrust to weight ratio of 5.6, this engine has already been used in the latest variants of the RQ4. Just weeks prior to this presentation, Rolls-Royce announced its successful initial testing of the first commercial scale hydrogen turbojet engine. The turbojet engine core of this engine would just so happen to be the very same used in the AE 3007 turbofan.
The drag over velocity range calculation acts as predicted, and after some tweaking of the cruising thrust, the velocity at that point is larger than the cruise velocity.
With a wing and mast model built in XFLR5, we were able to experiment with CG placement, which resulted in a negative slope on a moment coefficient over angle of attack plot. This negative slope signifies longitudinal stability.
With spar-specific details on historical aircraft using hydrogen due to classified or trade secret contracts, it was challenging to anchor our concepts. With a great number of design loops, we could achieve refinement of our concepts, including analysis done in XFLR5.
Liquid hydrogen is able to store over 3 times more energy per weight than jet fuel, but takes up nearly 3 times the volume. With this in mind, we were able to boost the loiter time of an RQ-4 Global Hawk by over 2.5 times by adding additional fuselage-mounted wing tanks. These modifications result in maintaining many of the standard specifications with the exception of a greatly increased endurance and complete reduction of carbon emissions. Any questions?